I am now going to show you the Python discretization functions of Laspated library. Let us go to the discretization folder of Laspated library, which is called discretization. And let us install the Python libraries that are needed for Laspated. So Python -m pip install, let us install pandas, GeoPandas, Matplotlib, NumPy, and H3, where H3 is a Uber space discretization library used by Laspated. Let us open the Python command window and let us import these libraries. So pandas as PD, GeoPandas as GPD, Matplotlib, NumPy as NP, and finally, let us import our Laspated library. The discretization module of Laspated library discretize in space and time observations for which we have a timestamp, a time information, a location information, plus additional features. To do this, we need to create a data aggregator object of spatial and temporal information. This is an object that will store data of spatial and temporal discretization. And to initialize this data aggregator object, we must first specify the CRS, the coordinates reference system used to locate data. The usual way of representing locations is with latitudes and longitude. So let us see in this situation how to initialize the data aggregator object. The data aggregator object will be called app, and it will be initialized with method data aggregator of Laspated library. So we initialize the data aggregator object as follows: app is Laspated.data aggregator, and we need to specify the CRS with the usual way of representing locations with latitude, longitudes. We use for CRS EPSG 4326. So now we have a data aggregator object. And we need to attach, to associate to this data aggregator object our events, the events for which we want to do time and space discretization. In this presentation, to illustrate the functions, the discretization functions of Laspated library, I will use the data of emergency calls to Rio de Janeiro Emergency Health Service. More precisely, the corresponding file, contains the history of emergency calls for the years 2016 and 2017. Now let me show you this file. This is a CSV file that is called emergency calls Rio de Janeiro.csv. You can find this file in the folder data of the GitHub page of Laspated library. The first line gives a description of all the columns. And then every subsequent line corresponds to an emergency call. So let us see what we have in the first line. The first column gives an index of the call. The second column for these emergency calls will give the priority of the call. So here you can see prioridade in Portuguese. This priority is an integer, 0, 1, 2, 3. Then in the third column, we have the latitude of the call. In the next column, we have the longitude of the call. In the next column, we have the date of the call. In the next column, the time of the call. And in the last column, we have an aggregated time information that contains both the date and the time of the call. So as I was saying, after this first line that describes the columns of the CSV file, every line corresponds to a call. So for the first call of this history of emergency calls, we see that we have a call of priority 3. The latitude is -22.86, etc. The longitude -43.33, etc. The date is January 1st, 2016. This is the time, 2 hours, 9 minutes, 13 seconds. And the last column is the column that aggregates the date and time information, and so on for the subsequent lines. So what will Laspated do for space and time discretization? Basically, it will add columns corresponding to the space and time discretization. So as we have seen, we have created a data aggregator object that we called app. We will associate our events. In the case of this example, these emergency calls to the data aggregator object. So corresponding to this data aggregator object, after associating these events to the data aggregator object, we have these columns that you can see here in the CSV file. And after the space discretization step, we will add a new column. And this new column will give an information of space discretization. So let us assume that the data is contained in a rectangle. And to start with a simple example, that we divide this rectangle into 100 subregions that are rectangles. So let us say that these rectangles are indexed from 0 to 99. So 0, 1, all the integers from 0 to 99. So in this situation, after the space discretization step, Laspated will add a column to the data aggregator object that will give for every call the index of the rectangle where this call is. So assume that the first call is in rectangle with index 3. In this situation, we will add in the column that we add corresponding to space discretization, we will add in this line the number 3. If the second call is in region with index 34, we will add for the column of space discretization 34, and so on. And we do the same for time discretization. So for time discretization, as an example that we will use later, assume that we want to do a time partition for every day of the week into time windows of 30 minutes. So to index a time window of 30 minutes during the week, we can use two indexes. The first index corresponding to the day of the week. We have 7 of these indexes for the 7 days of the week. So let us say that this index will be an integer from 0 to 6. And then for a given day, we can index the time windows of 30 minutes during this day by an integer between 0 and 47, since we have 48 time windows of 30 minutes during the day. So in this situation, for the time discretization, we would add to the data aggregator object, and in fact, to this file, if you wish, that contains the same information, we will add 2 columns, one corresponding to the day and one corresponding to the time window of 30 minutes during the day. So here for this first emergency call, in the first column, we have to see what is the day corresponding to January 1st, 2016. This day will have a given index that will be added in the column of time discretization corresponding to the day. And then for the column corresponding to the index of the time window of 30 minutes during the day, then we see here that the call is at 2 hours, 9 minutes, 13 seconds. So this is the 5th time window of the day of 30 minutes. So if the indexes start at 0, as I was saying, so the index will be 4 here for the time window of 30 minutes during the day for this first emergency call. So basically, this is what will be done by Laspated space and time discretization functions. And let us now see the details of these functions. And let us see how to call the corresponding Python Laspated functions to build the space and time discretization. So for that, let us go back to the Python command window. Now that we have created the data aggregator object, I need to associate to this data aggregator object the events. In my example, as I was saying, the events will be the emergency calls to Rio de Janeiro Emergency Health Service for years 2016 and 2017. Let us call events these events. These events are contained in a CSV file that I have shown you that we will read with read CSV panda function method. So PD read CSV, and I need to give here the path of the file containing these emergency calls. You can find this file into the folder data of the GitHub page of Laspated project. And the name of the file is emergency calls Rio de Janeiro.csv. Then we need to add these events to the data aggregator object. We now add the events to the data aggregator object app.add events data events. So the name of the column for the timestamp is data hora. The name of the column for latitude in the CSV file is lat. The name of the column for longitude in the CSV file is long. And the additional columns for features, actually there is just one column, which is the column for priority, and it is called priority Dutch. And we need to specify the datetime format, which is months, day, year. So months, day, year, and then hour, minutes, seconds. So now we have added the events to the data aggregator object app. We will now see how to define space discretization. The first step is to define borders for the region to be discretized, which contains the observation. And we have three options for that. The first option uses a customized border given by a shapefile. The second option will use a rectangle that contains the observations. And the third option will use the convex hull of the observations. So let us start with this last possibility. Let us use as the region that contains the observations the convex hull of the observations. For that, we use the method add max borders of Laspated. So this method add max borders of Laspated will be used to define the border, the region that contains the observations, and it has an argument method, and there are three options, as I was saying. And when we want to use as the region that contains the observation, the convex hull of the observations, then this argument method needs to be the string convex. So this command, app.addMaxBorders method is convex, will build the convex hull of the observation. We need to have the events already defined in the data aggregator. It may be slow when many events are added. So let us check that this worked, representing the convex hull of the observations and the observations. Now we will also represent the events. on the same figure. And for every call, we will use marker size, say, of 10. We will use a red color. And now let us represent the convex hull of observations and the events. So let me show you this. Here is the corresponding figure. You can see here in blue the convex hull of the observations. So these observations, I recall you that this is data of emergency calls to Rio de Janeiro city for years 2016 and 2017. And you can see in red the emergency calls. So now what we are going to do is we are going to use Laspated space discretization functions to discretize in space in 3 different manners. So first in rectangles, second in hexagons, and then using a customized discretization that could be any customized discretization provided by the user. And in our situation, we will use the district of the city that will be given as a shapefile. So the borders of the district will be given by a shapefile. So let us see how to do this. So let me go back to the Python command window. And let us start adding rectangular discretization to this convex hull of the observation. So a rectangular discretization of the studied area, in our case here of the convex hull of observation, is obtained using Laspated method add geodiscretization and specifying the value R for the parameter disc type and providing parameters that will define the horizontal and vertical discretization step. So let me show you how to do that. So app is our data aggregator object. For space discretization, we will use Laspated method add geo discretization. And as I was saying, this method has several arguments. The first one is disc type, the discretization type. We have 3 possible values. And if we want a rectangular discretization, we will use the string R for rectangular for the argument disc type. And then, as I was saying, we have 2 additional parameters. These are rect disc param x, and we have rect disc param y. So rect disc param x and rect disc param y define the horizontal and vertical discretization step. For instance, to generate a discretization into 10 by 10, that is to say 100 rectangles, we use 10 for the horizontal discretization step and 10 for the vertical discretization step. And to check the corresponding discretization, we can, to represent the corresponding discretization, we will use app plot discretization. Let me show you the corresponding results. This is what we obtain. So as you remember, the studied area is the convex hull of observations. And we have discretized this into rectangles here. And we have put here into every rectangle its index, starting from 0, 0, 1, 2, 3, and so on, until seemingly 79. So now let us go back to the Python command window. And let us see how to discretize into hexagons. So Laspated also provides an hexagonal discretization of the studied area. This discretization is again obtained with Laspated method hagiodiscretization. Now specifying H for parameter disc type. So I will reuse this hagiodiscretization method. Instead of R now, I will use H for hexagonal for the argument disc type. And now the second parameter is a scale parameter taking values between 1 and 16, where the smaller the integer, the coarser the discretization. So the second parameter is called x disc param. And let us take the value 7 for this parameter. And again, we can plot the corresponding discretization with the same method as before. I will show you the corresponding results. This is the discretization that we obtain. So you see that you remember that the studied area is the convex hull of observations. And now we have divided this area into hexagons. And into each hexagon here, in this representation, we have written the index of the subregion of the hexagon. So now let me go back to the Python command window. And let us see the third way of defining space discretization with Laspated. So far we have seen rectangular discretization, hexagonal discretization, and we can also have customized discretization. So the user can provide also a shapefile of subregions. So first, in this situation, a geodata frame object containing geometries of each subregion needs to be provided. For instance, still using our example of emergency calls to the emergency health service of Rio de Janeiro, we can provide as subregions the district of Rio de Janeiro. In the folder data of Laspated project, that you can find on the corresponding GitHub page. You can find a subfolder Rio de Janeiro neighborhood that contains a shapefile of the district of Rio de Janeiro. So if we want to discretize in space using the district of the city of Rio de Janeiro, we first need to read the corresponding shapefile. So let us call custom map the corresponding geodata frame object that is obtained with function read file of GeoPanda, gpd.read file. And here I will provide the path of the shapefile that contains the district of Rio. Again, that you can find on the GitHub page of the project. And this is, as I was saying, in folder data and in subfolder Rio de Janeiro neighborhood. And the name of the shapefile is Rio neighborhoods.shp. Here is missing an O. Fine. So again, we specify the CRS. So custom map set CRS EPSG and now the space discretization is obtained again with method @geodiscretization, specifying say as disc type parameter and the geodata frame object of the subregion as the additional parameter custom data. So let us go back to the previous comment where we did the hexagonal discretization. Here, we need to replace the disc type parameter with the value C for customized. And we need to specify the geodata frame object corresponding to the shapefile of the subregions. So custom data is what we defined as the geodata frame object of the subregion. This is custom map. And again, we can visualize the corresponding space discretization with the plot discretization function. I will show you the corresponding output. So here you can see a space discretization of the city into its district. And in this situation, what Laspated will do, it will count the number of observations in every district. And then when we use time discretization, we will also count for every time partition and also for every subregion, the number of calls. So we have seen how to do space discretizations of 3 types in rectangles, hexagons, and customized. When the border that is used, the region that contains the information that is used, is the convex of observations. We can do the same, taking a rectangle that contains the observations as the border of the studied area. So let us see that. Let us go back to the Python command window. So now we need to define as the region that contains the observation a rectangle. So we still use the add max borders method of Laspated. So we will do app.add max borders. The argument of method now is rectangle. Again, the events need to be defined before in the data aggregator object. And we are going to represent, as before, this region that is now a rectangle containing the observations as well as the events. So app.max borders.plot. Let us represent the events with markers of size 10 as before. Let us use for these events the red color. And let us visualize the corresponding output. I will show you the results. So now we use a rectangle as the border of the studied area. This is now the region that we are going to discretize, and still we represent in red the events individually. So let us go back to the Python command window. And we are going again to discretize in 3 different manners this studied area in rectangles, hexagons, and customized using the districts. The comments are the same as before. The add geodiscretization method of Laspated. So for the discretization in rectangle, we used this command here that we repeat to obtain a discretization in rectangles of the rectangle that we have defined that contains the observation. So here, the discretization is in 100 rectangles. And we can see the corresponding result using the plot discretization function again. Here it is. And I will show you the output. So as you can see here, we have discretized the big rectangle that contains all the observations into 100 rectangles that have indexes from 0 to 99. Let us go back to the Python command window. We can still discretize the studied area into hexagons as before, but now instead of discretizing the convex hull of observations, we will discretize the big rectangle that contains the observations, but the command is the same using discretization. So this command was this command of discretization. So we use the discretization method of Laspated. And we can, with plot discretization, visualize the corresponding discretization. I'm going to show you this. Here it is. So you can see here that we have discretized the rectangle containing the observations into hexagons. And into every hexagon, I have its index. Let us go back to the Python command window. And finally, let us see how to discretize the rectangle containing the observations into the district of the city. And this is done as before with the method discretization with the disc type argument being C for customized. Here it is. And again, we can visualize the corresponding discretization with the plot discretization function. I'm going to show you the corresponding result. Here it is. You can now see that we have discretized the rectangle containing the observations into the district of the city. And inside each district, we have its index. Let us go back to the Python command window. And finally, let us see the discretization steps when we define as the border, as the region containing the observations, a customized region. In our case, it will be the city of Rio de Janeiro, since the emergency calls are for the city of Rio de Janeiro. So to use the city of Rio de Janeiro as the region containing the observations, we still use the add max borders method of Laspated, and we need to provide as argument max borders the geodata frame object corresponding to the shapefile of the city. So this max borders geodata frame object will be obtained with method read file of GeoPanda, and we need to provide the path of the corresponding shapefile. It can be found in the folder data subfolder RJ of the Laspated GitHub project, and the name of the shapefile is rj.shp. And then we add the region containing the observations using the add max borders method with this argument max borders. We can again plot the region containing the observations. This region is now the city of Rio de Janeiro, together with the events, that is to say the emergency calls. So PLT subplots. Let us, as before, represent the events with markers of size 10 of color red, and let us visualize the corresponding region with the events, the calls. Let me show you now what we obtain for the region containing the call. This is the city of Rio de Janeiro, and in red, the calls that are represented individually. So now what we are going to do, we are going to discretize this region. Now this is the studied area in three different manners as before, in rectangles, hexagon, and using a customized space discretization, namely using the district of the city. And this will be done using the same commands as before. Let us go back to the Python command window. So now we have defined our border, the region containing the observations. This is the city of Rio de Janeiro. Let us add a rectangular discretization. This is the command that we used before to discretize in 10 by 10 rectangles. We can do the same now. And use again plot discretization to visualize the corresponding discretization. Let me show you the result. Here it is. You can see now that the border is the border of the city of Rio de Janeiro. And we have discretized it into rectangles. So we see here that we have 76 rectangles indexed from 0 here in the bottom left corner to 75 here in the upper right corner. So let us go back now to the Python command window. We can discretize the city of Rio de Janeiro into hexagons. And this is done as before with Laspated command add geodiscretization with the disc type parameter being h. And again, we use the plot discretization method to visualize the corresponding discretization. Let me show you the output. So you can see here the city of Rio de Janeiro discretized into hexagons. And we will use these hexagons for the space discretization to count the number of calls that we have in every hexagon. And then further in every hexagon and in every time window of the time discretization that we will define later. And we can also discretize the city into its district. So we can use a customized discretization using, for instance, as the customized discretization, the district of the city. And the district will be given by a geodata frame object corresponding to a shapefile of the district of the city. So we have seen how to do this before. We first read the shapefile corresponding to the district of Rio. We define the CRS. We use the add geodiscretization method with the discrete type argument C and specifying for custom data the geodata frame object corresponding to Rio de Janeiro shape file of the district. And we can visualize the corresponding discretization. This is a discretization of the city into its district. So far we have seen how to define a border of the studied area, a region that contains all the observations, and how to discretize this region either in rectangles, in hexagons, or using a customized discretization. I am now going to show you 3 additional space discretization functions offered by Laspated. These functions apply when we have 2 different discretizations. And to describe these functions, I am going to use again the project that motivated the development of Laspated library, which is the calibration of statistical models for the process of emergency calls to Rio de Janeiro Emergency Health Service. For these emergency calls, in the context of this project, we have proposed 2 models. These models are based on a discretization in space and time, more precisely for the subregion I, for the time window T, and for a call of type C. We assume that the process of calls is Poisson with some intensity lambda CIT that depends on the call type C, on the subregion I, and on the time window T. For the calibration of these intensities lambda CIT of the Poisson processes, we have proposed 2 possibilities: a calibration using a regularized likelihood, and a model using covariates, where the intensities are linear functions of some covariates. In the context of our project of calibration of models for emergency calls, we have used as covariates the population and a certain number of lump types. So in this situation, the intensities are linear functions of the population and of the areas of a certain number of lump types. For instance, we could consider as lump types lakes, the forest, residential area, and industrial area. So for this project, we had for our covariates, actually on top of the discretization defined by the user, 2 additional discretizations. A discretization for the population information and a discretization for the lump type information. More precisely, the population was given for every district. And for the lump types, we had another discretization. We had 16 different land types. And for this discretization, a given cell of this discretization was of a given land type. In this context, Laspated provides two functions. A first function that allows to compute the population in every discretized cell of the user-defined discretization and the areas of the different land types in the regions of the discretization defined by the user. So to exemplify, assume that the user chose an hexagonal discretization. It was obtained before with this comment. So let us build again the hexagonal discretization. Let us visualize it again. So we assume that the user wants this discretization for the calibration of emergency calls, and more generally for the calibration of statistical models for stochastic spatiotemporal data. So we have here this hexagonal discretization. And for the model with covariates, in the context of the calibration of emergency calls, we would like to know the population for every hexagon. And for every hexagon also, we would like to know the areas of the different land types. So if we take the 4 land types that I mentioned before, we would like to know in every hexagon of the discretization defined by the user, we would like to know the area of lakes, of forest, of residential area, and of industrial area. So let us see how to do that with Laspated. Let us go back to the Python command window. We are first going to read the population information. So let us call population the corresponding geodata frame object. You can find on the GitHub page of the Laspated project a shapefile of the population in district of Rio de Janeiro. Let us read this shapefile. So with the GPD read file method, let us provide the path of the shapefile of the population of the district of Rio de Janeiro. So it is in the folder data, subfolder regressores, subfolder população, population in Portuguese, and the name of the shapefile is population.shp. Let us filter the columns of interest, which are population and geometry. So now we have 2 discretizations of the city of Rio. The first one is an hexagonal discretization that was defined by the user for the calibration of statistical models for the process of calls. In this situation, we will have Poisson intensities for every hexagon of the discretization, every time window, and every arrival type. And we have a second discretization by district, and the corresponding geodata frame object is population here that provides the population by district. Now, if we want to get the population for every hexagon of the user-defined discretization, then we use the addGeoVariable method of Laspated. So app.add geo variable. Population is the second discretization. And we have a second parameter, which is type geovariable. Which needs to be feature. And now, with the print app geo discretization command, we have an aggregated information now. We have enriched the information with the population information. So for every hexagon, now we know what is the population. So you can see here in every line corresponds to an hexagon. We have 226 hexagon. And for a given line, we have the index of the hexagon, the indexes of the neighboring hexagons, the coordinates, latitude, longitude of the centroid of the hexagon, and the population. So more generally, with Laspated, we can do the following. Let me show you this slide here, where we describe more generally the add geovariable methods of Laspated, when the second argument, type geovariable, is feature, which is the value of the argument type geovariable that we have used. The first argument of add geovariable is a geodata frame object corresponding to another discretization. In our case, it was the discretization in district for which we have the population. So assume that we have a discretization D2. In our case, it was by district. And for every region J of this discretization D2, we have a density dj of some attribute. In our case, it was the population. We assume that the attribute, in our case, it was the population, is uniformly distributed in the region. Then in this case, the attribute pj is the density dj times the area of region j. Now, Laspated, with this method add geovariable, allows us for every subregion I of the first discretization to obtain the value of the attribute in the region. And how is it computed? Very easily. So for every region J of the second discretization D2, we compute the area of intersection of I and J, and we multiply this area by dj, since for the region corresponding to this intersection, the density of the attribute is dj. So the value of the attribute in the subregion I of the first discretization is the sum over j of dj times the area of the intersection of the subregions I and j from the first and second discretization. And then we substitute, if what is known are the attributes pj, we substitute dj by pj divided by the area of j. Now let us go back to the Python command window. I am now going to show you how to compute the area of every land type for every hexagon of the discretization that we chose to compute the intensities. We first need to read the shapefile containing the land type information. Let us call land use the corresponding variable. We use the read file method of GeoPanda. The shapefile can be found on the GitHub page of the project, and it is in folder data, subfolder regressores, subfolder uso do solo, and shapefile is called uso do solo.shp. Then we filter the columns of interest. We are going to consider 4 groups of land types. Called subgroup 0, 1, 2, 3. Subgroup 0, subgroup 1, 2, 3, and let us filter the geometry. And now to compute the area of every land type in every hexagon, we use the add_geovariable method of Laspated. So app.add_geovariable, and there are 2 arguments. The first one is the second discretization, the discretization corresponding to the land types. So this is given by the geodata frame object land use. And we have a second variable, type geovariable, which needs to be area. We can visualize the area of every land type for every hexagon and the population of every hexagon using the geodiscretization method of Laspated. So let us print this information. Print app geodiscretization. And let us show for every hexagon its index, the area of the first group of land types, so subgroup 0, and the area of the land types of the other subgroups 1, 2, 3. Subgroup 0, 1, 2, and 3. And finally, we will show the population for every hexagon. So here it is. We see that we have 226 hexagons in our discretization, and a given line here corresponds to an hexagon. We first have in the first column the index of the hexagon. Then in the next 4 columns, we have the areas of land type groups 0, 1, 2, 3. And in the last column, we have the population in the corresponding hexagon. Now let me show you how to generalize this and how to use the geodiscretization method of Laspated with the type geovariable area in a slightly more general context. So we consider the add_geovariable method of Laspated. And what we have on top of the discretization defined by the user is a second discretization that we call D2 here. And what we would like to do is the following. For this second discretization D2, the subregions of this discretization are subregions of, say, K types. So in the context of our project of calibration of emergency calls, K was initially equal to 16. We had 16 different long types. This information was further grouped into 4 groups of long types. For instance, we could consider lakes, forest, residential area, industrial area. So here for our second discretization, say D2, we have the K types, little K types of subregions. And correspondingly, we have a partition of the set J of subregions into K groups of subregion. And in a given group, I, we put all the regions of type I. Say in a given group, all the subregions are of the same type. And what the add-geovariable method of Laspated with the type geovariable area does is the following. It computes for every subregion I of the first discretization. In the case of our previous example, it was for every hexagon. So it computes for every region I of the first discretization. And for every type, every long type L, it will compute the area of long type L for the subregion I. So we call this here AIL. And how this is obtained? Well, we need to consider, since we are interested in long type L, we need to consider for discretization D2 the subregions that are of type L. And these subregions are in the group JL. So what we do is for all these region J of type L, we will compute the area of intersection of this region J with the subregion I of the first discretization. And then we just need to sum the areas of intersection of the region I with every region J of type L. This will give us the area of long type L for region I. Now let me go back to the Python command window to show you the third and last space discretization function offered by Laspated. As you have seen, for the first 2 additional space discretization functions that we have commented to compute the population and the land type areas for every hexagon, we have used the area of intersection of every pairs of regions from the first and second discretization. And precisely the third space discretization function of Laspated that I would like to show you is the method getIntersection that computes for every pairs of regions for I and J from the first and second discretizations the area of intersection. So the getIntersection method can be used to obtain these areas of intersection. And we need to pass as arguments the 2 discretizations that we are interested in. So in our situation, we could, for instance, compute the areas of intersection of all the hexagons of the first discretization that we have defined to calibrate the intensities with the discretization that was used for the population, and we record that this is the discretization by district. So this get intersection method that takes as parameters two geodata frame objects that are the two geodata frame objects of the two discretizations we are interested in, will return an array that will give us, for every pair ij of subregions, I from the first discretization and j from the second discretization, the area of intersection of these subregions.